Dear students, so here we shall see the proof of Lebesgue number lemma. Now before going to the proof of this lemma, we need few basic definitions. So let's start with the basic definitions. So first of all, we need the concept of distance. So of course, if we know X is a matrix space, we know the distance between 2 points, right? It is just d of X and Y, right? Now we shall define what is a distance between a point and a set. So let XD be a matrix space. Now let A be a non-empty subset of X. Here in this talk, we always assume that the subset or the set is non-empty. So even if I miss the term non-empty, but you can always assume that the set is non-empty. Fine. So here we first take X is a matrix space and A is a non-empty subset of X. Now for each point X, we define the distance between the point X and the set A, or we can say the distance from X to the set A is defined by the equation. So we denote it is by dx and capital A. That's mean the distance between the point X and the set A, and it is defined by infimum of d of x comma A, where A belongs to A. That's mean we first take a set in R, which is the distance between X and a point A for all A belongs to the given set, and then we take the infimum. So that's mean, so suppose we have the set, for an example, let A is my set X comma Y, which is belongs to R2, such that x square plus y square less than 1. That's mean this is my unit circle, right? So this open one, that boundary is not included, and say x equal to 2 comma 0. So this one 2 comma 0. Now if you choose any point in this set A and if we find the distance, you will get a real number, right? And if we take that collection of those real numbers and if we take the infimum, then we can easily see that that infimum will be 1. So this will be that. Now in this case, d of x comma A will be 1. Note that the point satisfies this equality here. The point is 1 comma 0. So distance between 2 comma 0 and 1 comma 0 is actually 1, but that 1 comma 0 is not in the set A, right? That is the reason we have taken the infimum, not the, because the smallest value may not exist, but in this case we always take the infimum. Fine. Now there is another concept called diameter of a set. So diameter of a set. So again let XD be a metric space and A be a non-empty subset of X, then the diameter of A is defined by so in this case we take supremum of D of A1 comma A2 where A1 A2 belongs to A, and we will denote by DA. So this is just a notation. So different book uses different kind of notation. So here I use just D of A. That's mean diameter of A. So that's mean again if we take the set A is my unit disk, open disk. So x square plus y square less than 1. That's mean this disk, right? Now if we choose the point, suppose this is my line, so this point and this point, then this will be the distance. And if we take this point and this point, so this should not be the boundary. So this is the distance, and if we take the supremum of this value, you can find that diameter of A equal to 2. Again, you can check that there is no pair of points in A which satisfies this inequality, but still the diameter is 2 because we have taken the supremum. In other words, if we take the point, say my n equal to say 1 by n, say 1 minus 1 by n, comma 0, and if we take bn equal to minus 1 plus 1 by n, comma 0, now you can find distance of an and bn is, what is the distance between these two? You can check the distance is 2 minus 2 by n, right? And if we take the supremum of this, that will be 2. So here an and bn belongs to A, right? And the distance is 2 minus 2 by n. But if we take the supremum of this set, then it will be 2. So the diameter is 2. Fine. Now we have another observation. So let XD be a metric space and A is a subset of X. Again, we assume non-empty. As I told you, that you have to always assume that all the sets are non-empty here, even if I do not specify that. Now, if we define a function f from x to r, so it is defined by f of x equal to d of x comma a, right? Then you can check that f is continuous. In fact, you can easily prove that it is uniformly continuous. F is uniformly continuous. Okay, so here we shall prove this. So first of all, we choose two arbitrary points x and y from my whole space X. Okay. Now what is my d of x comma a? Now this is the infimum of d of x comma small a, where small a belongs to the set capital A, right? So we can easily write that this is less than equal to d of x comma a for all a belongs to A, right? Now we can use the triangle inequality. Now this term is also less than equal to d of x comma y plus d of y comma a, and this is true for all a belongs to A. Now that implies d of x comma a minus d of x comma y less than equal to d of y comma a, and this is true for all a belongs to capital A, right? Now note that the left hand side, this one is independent of the choice of A, right? It is independent of the choices of the point A. So that's mean we can take the infimum in the right hand side. So that implies d of x comma a minus d of x comma y, it is less than equal to infimum of this d of y comma a, and this is just d of y comma set A, right? Now that will imply d of x comma a minus d of y comma a less than equal to d of xy, right? Now if you interchange x and y, you will get d of y comma a minus d of x comma a less than equal to dxy, because dxy equal to dyx, right? Now that will imply mod of dx comma a minus d of y comma a, that is less than equal to d of xy, right? We can write this one. So by interchanging x and y. Now what is my this one? So this is my fx and this is my fy, right? So that imply mod of f of x minus f of y less than equal to d of x comma y. So this is the condition for uniform continuity, right? So that imply f is uniformly continuous, right? So we shall use this observation to prove the Lebesgue number lemma. Now again, I want to state another lemma which is also very useful for the proof, that says so we can write it is as a lemma. So let X be an ordered set with ordered topology. Now then any non-empty compact subset A has the smallest element and largest element. So this is simple. That's mean if you have an ordered set with ordered topology, then you can see that if you have any compact subset, say A, then that A contains its smallest element as well as its largest element. For an example, say X is R, okay, that's mean real line with usual topology. So with usual, or we can say order topology. So we know that in R, usual topology and order topology are same, right? Now if we take the set A is my open interval 0, 1, obviously this is not compact, and we can check that A does not have any smallest element and greatest element, right? But if we take A equal to open interval 0, 1 union say -1 and 2, this set, then again A is not compact, but then A is not compact. This case also A is not compact, but A has smallest and greatest element. That's mean if we have a non-compact set in a ordered set X, then we cannot say anything about the smallest element or greatest element. That's mean the smallest element and greatest element may exist or may not. But if we choose, this lemma says if we have compact set, then it must have the smallest element and the largest element. And here is the proof. So let A is be a compact subset of X. Obviously, A is non-empty. We assume that it is non-empty. Okay. Now first we assume that A do not have any smallest element, and then we will get a contradiction. So assume, or you can say if possible, A do not it does not have any smallest element. Okay, so we assume that A is a compact subset of X and A does not have any smallest element. Now take this collection, say script A, which is open interval A comma infinity, where A is from the set A. Now claim that script A is an open cover of A. So to show that A is that script A is an open cover of A, we have to check that all the elements of the script A is open and it covers A. Now obviously these are the open sets, so we need to check this covers A. That's mean that is for each point x belongs to A, there exists some element, say A alpha belongs to that set script A, such that x belongs to script A. Sorry, x belongs to A alpha. So we need to check that only, right? Okay. Now let x belongs to A. That means x is an arbitrary element of A. Now it is given that A does not have any smallest element. Now since A does not have any smallest element, that implies x is not the smallest element of A. So that is, there exists A belongs to the set A such that A less than x. Obviously x is not the smallest element. That's mean there will be another element A which is less than A, right? Now that imply x belongs to A comma infinity, and this is an element of the script A. Now that imply script A is an open covering of the set A, right? Okay. Now we use the fact that our set A is compact. Now since A is compact, so there exists a sub-collection. We can give the name of that sub-collection, say A1 infinity, A2 infinity, say AN infinity. This is the sub-collection of the script A which covers A, right? Why? Because this is the definition of a compact set. So A is a compact set, and script A, which is this collection is an open cover of A, right? Therefore, we have a finite subcover of A. That is, we have a finite subcollection of the script A which covers A. Now, we choose the smallest element of A1, A2 up to AN. So let AK equal to minimum of A1, A2 up to AN. That's mean AK less than equal to AI. Now, see, this is a sub-collection. This sub-collection covers A, right? That's mean for any A, so there exists I between 1 to N such that A belongs to AI comma infinity, right? This is true. Why this is true? Because this sub-collection covers A. That's mean whenever we have an arbitrary element small a, so there should be an element of this finite subcollection, say AI comma alpha, this open set, which contains A, right? And this A alpha, that this AI is just from A1, A2 up to AN. Now from this, we can say AI strictly less than A, right? Because A belongs to the open interval AI comma infinity. That's mean AI strictly less than A. But we also know that AK less than equal to AI, because AK is the minimum of this, and this is strictly A. Now that implies AK less than A for all A belongs to A. So whenever you choose any arbitrary element A, then AK should be less than A. And this contradicts the fact that AK belongs to A. Now this contradicts that AK belongs to A. Right? Did you get the contradiction? See, whenever we have any arbitrary element A, we always have AK strictly less than A, right? But we know that AK belongs to A because all the element A1, A2, in fact, all the element here, this is belongs to A. Now, since we have a finite subcover of this one, that's mean all the A1, A2 up to AN belongs to A. In particular, AK belongs to A. Now, since AK belongs to A, so if we put AK here, that's mean AK strictly less than AK. And that is the contradiction. So since AK less than AK. So this is the actually contradiction. Fine. So that's mean it says, so what was our condition? So we assume that if possible, A does not have any smallest element. So we assume that A does not have any smallest element and we get a contradiction. That's mean A must have a smallest element. And similarly, you can prove that A must have a largest element. In that case, you can choose your this collection as minus infinity comma A. So similarly, you can prove the set A has largest element. And this is the hints. If you want to prove, you can consider the proof will be the almost same, and you have to choose this script A will be minus infinity A, where A belongs to A. And if you choose AK, will be the maximum over A1, A2 up to AN. So this is the hints. So if you only change this one and just the smallest, you just have to replace the smallest by the largest. So that's all. So you can easily prove this one. And as a corollary, you can say any compact subset, obviously non-empty, any non-empty compact subset of R has the smallest and the largest element. Why? Because R is an ordered set with ordered topology. That's mean if we take the usual topology on R, which is same as the ordered topology, you can prove that any compact subset has the smallest element and the largest element. In fact, when you have R, that is if you assume R, you can prove this corollary directly as well, but in that case, you have to use the completeness property of R. Alternately, you can use completeness property of R and that least upper bound property and greatest lower bound property. So if you use these properties, then you can get the proof of this corollary directly. And you have to also use the fact that any compact subset in R or any compact set in R is actually closed and bounded. And also this one, compact imply closed and bounded. So by using this fact, you can also prove this corollary directly. Otherwise, I always prefer this proof because here you do not have to use any property. It uses only the compactness. And I always prefer this proof. Okay? Okay, fine. So now we are ready to state and prove the Lebesgue number lemma. And here is the Lebesgue number lemma. So now this lemma says, let Xt be a compact metric space then, so if we take an open covering, say script A, open covering of X. Now then we always find one small positive number delta so there is a delta bigger than 0. So it can be the larger one as well, but it gives the guarantee that you always have a delta greater than 0. So you can choose a small one. So this theorem says, so then there is a delta greater than 0 such that for each subset of X having diameter less than delta, so there exists a delta greater than 0 such that whenever you have a subset of X whose diameter is less than delta, then there exists an element of script A containing it. In other words, we can say, so let X be a compact metric space and script A be an open covering of X, then there exists a positive delta such that whenever we have a subset B of X with diameter of B less than delta, then there exists an element A from the open cover, that is there exists an open set from the open cover which contains the set B, that is B subset of A. So this theorem says this one. Now the question is, why is compactness necessary? So why is compactness necessary? So what if you have a non-compact matrix space? So we choose let X equal to open interval 0, 1, right? And take the usual topology in R, or you can say usual subspace topology in R. Obviously then X is not compact matrix space with usual metric. Right? Now we can choose one open cover, this one, say 1 by n comma 1, where n belongs to n. Now obviously you can easily check that X is union of 1 by n comma 1, right? That is A is an open covering of X. Now you can easily check that Lebesgue number lemma does not hold for this matrix space. Why? Now let delta greater than 0, some arbitrary small number. Now take my set B equal to say 0 comma delta by 2, okay, and that implies diameter of B equal to delta by 2, which is less than delta, right? Now we claim that there is no element from A which will contain B, because any element of A is of the form one by capital N comma 1, right? For some n, this. So that's mean, so let we choose M which is bigger than n such that 1 by m less than delta by 2. Now that imply 1 by m is not belongs to this set, but 1 by m belongs to my set B. That imply B is not covered by any element of A, or you can say any single element. You can write any single element of A. It is clear, right? And this is true for any delta, and this is true for any delta bigger than 0. That's mean Lebesgue number lemma will not hold for this matrix space, and obviously this is not compact. Now we prove that if X is a compact matrix space, then we always have such a delta, and this is called the Lebesgue number lemma. So here is the proof. So proof of the lemma. So first of all, we already given that that script A is an open covering of X, right? Now if X itself is an element of A, that is element of the script A, then any positive number is a Lebesgue number for A, right? Why? Because if we choose any subset B, then B is always subset of X, and X is in my script A, that is in the open cover. So there is nothing to prove. So we assume that X is not an element of A. So we assume X is not an element of A. Now we will use the compactness of X. It is given that X is compact. So since X is compact, there exists a subcollection say A1, A2, AN of that script A, which covers X, right? So that's mean X is the union of I equal to 1 to N AI, right? So we use the compactness of X. Now since X equal to union of this, that imply if we take the complement of both sides, then that will be the empty set will be equal to intersection of I equal to 1 to N AI complement, that is X minus AI, right? Now this one suggests me one function. Why? Because if X belongs to X, then we know that this intersection is empty. That's mean there exists I such that X is not belongs to that set, right? Because if X belongs to all of this X minus Xi, then this intersection will not be empty. Now since this intersection is empty, so if we choose any X, then we always find one I where X not belongs to X minus AI, right? Therefore, so if we define this is as my Ci, that is the close, so this is open, so this is closed, right? And X is outside of this closed set. So that's mean distance between X comma Ci is positive. We will actually see this, why this is positive. Anyway, so this is positive, and this is the reason we can define a function f of X such that d of X comma C1 plus d of X comma C2 d of X comma Cn. We can define this function. So this is the main idea of the Lebesgue number lemma. Well, so we will see in details. So we do not need this part. This is just for your understanding. So we do not need this part. This is just for your understanding. So what we have, since X is compact, so there exists a sub collection, say A1, A2 up to AN of script A which covers X, right? Now we will define actually Ci, which is X minus AI. Now let Ci equal to X minus AI. Then obviously, then Ci is a closed set in X, right? And this is for I equal to 1 to up to n. Now define a function f from x to r by f of x equal to summation of I equal to 1 to n d of x comma ci divided by 1 by n. Now you can ask, why do we need to divide by this? So there is no speciality of dividing by 1 by n. If you define fx equal to only summation of this, then also it will work. And you have to do just a different manipulation later. That's mean. So anyway, I will come to this portion later. Okay, so for the time being, we can assume that fx equal to 1 by n summation of this. And first we prove this one, this lemma, and then I shall show you there is no importance of 1 by n. You can skip this 1 by n as well. Fine. Okay. Now first we claim that for any x belongs to x, f of x bigger than 0. Why f of x bigger than 0? We will prove now. So first of all, since x belongs to x and this collection A1, A2, AN covers x, so there exists I belongs to 1 to n. We don't know which I will work, but there exists a I from 1 to n such that x belongs to AI. Okay, now we know that AI is open. Since AI is open, so there exists a epsilon bigger than 0 such that B, that is the ball of radius epsilon and centered at x subset of AI, right? And then for any y belongs to Ci, what is Ci? It is just my x minus AI. This d of x comma y will be bigger equal to epsilon. So why for any y belongs to Ci, d of xi bigger equal to epsilon? Because if we can choose a different pen. So if d of x comma y less than epsilon, that will imply y belongs to the epsilon ball, right? And subset of ai. And since y belongs to ai, so y will not be in ci. This is a contradiction, right? So that's mean we have this. Now since d of x y bigger equal to epsilon for any y belongs to ci, so we can take, that's mean this epsilon will not depends on y, right? So we can take the infimum, so we will get d of x comma ci is bigger equal to epsilon. Note that here epsilon depends on x but not depends on y. Fine. Now what is my fx? So my fx is this. So my fx is this, right? Now if we take f of x, then we can find, see, this one. So what is my f of x? F of x is just 1 by n and summation of d of x comma c1 plus there will be some number x comma ci d of x comma cn. This, right? Now we know that always distance, this is bigger equal to 0, this is bigger equal to 0, and we have seen this is bigger equal to epsilon. So that implies f of x bigger equal to epsilon by n. But note that this epsilon depends on x, but that term is bigger than always 0. So now 0 does not depend on x. So that implies f of x bigger than 0 for all x belongs to x. So we are done. So that's mean we can say, in other words, f is a function from x to open interval 0 infinity. That's mean x is a function from x to r, but it will be lie on the right hand side of 0. That is, it is from open interval 0 and infinity. Now we have seen that the distance function is continuous. In fact, it is uniformly continuous. So here we do not need the uniform continuity, but we have seen that f is continuous. So we can write, we have seen that the distance function, say f of I from x to r defined by f of I x equal to d of x comma ci. So we have seen that these distance functions are continuous, right? And f is just summation of these distance functions. So thus f is continuous, right? We can write here as well, being a sum of continuous functions. Now f is continuous, x is a compact set. So what can you say about f of x? Now since x is compact, and f is continuous, that imply f of x is a compact set in R, right? And we have seen that since R has order topology, so fx has the greatest element and the smallest element. So does f of x has the smallest element? Say delta, right? Now we have seen that f of x bigger than 0, that's mean the smallest element is also bigger than 0. Now since f is a function from x to 0 infinity, or you can write f of x is always bigger than 0, that imply delta, which is the smallest element, is bigger than 0. Note that here we are writing greater than 0 because delta is the smallest element of f of x. It is not the infimum. If it was infimum, then it should be greater or equal to 0. Since it is the smallest element, so it should be bigger than 0. As delta is the smallest element of f of capital X. Right? We have delta. Now we prove that this delta is the Lebesgue number. So we prove that this delta is a Lebesgue number. That means we prove that if we have a subset in X whose diameter is less than delta, then there is an element from script A which will covers that single element will cover the set B. So this is my final claim. So we claim that if B subset of X with the diameter of B less than delta, then there exists, actually we will find the element from the finite subcollection only. So there exists I such that B subset of AI. So first fix a point x0 in B. Okay. Now then for any x in B, we have d of x0 and x, it is less than delta. Why this is less than delta? Because x0 and x both are in B and the diameter of B is less than delta. Therefore, d of x0 comma x is less than delta. And that will imply x belongs to the ball with centered at x0 and with radius delta. Right? This is a simple one. That's mean whenever we have x in B, then x will be in this ball. And that will imply B is subset of this ball. Fine? Okay. Now, on the other hand, what is my f of x0? Now f of x0 is a value of x at x0, and what is delta? Delta was the minimum value, that is the smallest values of f of x. That means this is always bigger equal to delta, right? Now what is my f of x0? And f of x0 is just 1 by n, and the summation of d of x0 comma c1 plus d of x0 comma c2 and up to d of x0 comma cn, this one. Now what we will do, we will take the maximum of all of these numbers. Suppose this is d of x0 comma cm for some n, okay, then that will be less than equal to 1 by n d of x0 comma cm plus d of x0 comma cm x0 comma cm, and that is just 1 by n into n d x0 comma cm equal to d x0 comma cm. What is d x0 comma cm? As I told you, that d of x0 comma cm equal to maximum of all of these values, that is d x0 comma c1, d of x0 comma c2 up to d of x0 comma cn. Fine. Okay, so we have delta which is less than equal to f of x0, right, this one, and x0 is less than equal to d of x0 comma cm, that is d of x0 comma cm is bigger equal to delta. We will use this fact. Okay, now we claim that the final claim, this ball subset of am. What is am? That is x minus cm. See, note that why this is my final claim, because we have already seen that b, we can take it, choose a different pen, right? We have already seen that b subset of this ball. Now if we can show that this ball is subset of am, that's mean b will be subset of am, and that was the claim, right? That was the required condition. Fine. So we will prove this one only. So first of all, choose y belongs to this ball. What does it mean? That implies d of x0 comma y, that is less than delta. Now that will imply y is not in cm. Why? So if possible, y belongs to cm, then d of x0 comma cm, that will be less than equal to d of x0 comma y, right? Because y belongs to cm. So this is less than equal to this, and this is less than delta. That is d of x0 comma cm less than delta. But we have already seen that in the previous page, d of x0 comma cm, this is greater equal to delta. So This is a contradiction. Therefore, y not belongs to Cm. Now, since y not belongs to Cm, that implies y belongs to Am, as Cm equal to x minus Am. So we have chosen one arbitrary element from BD x0 comma d, and we get y belongs to Am. Now that implies this ball subset of Am. Thus B, we have already proved that subset of this ball and this ball subset of Am. Therefore B subset of A. Now this is the final answer. So this proves the lemma. Fine. Actually, the proof of this lemma is not the difficult one. So what was the main tricky part? Main tricky part is this one, the choosing of this function. This function. So this is the main tricky part. Again, if you see closely, then this is also not a tricky one, because this comes from this. We have explained this one, right? So x is union of this one, therefore this intersection will be empty. So we always have, if we choose any x, then we have always have some ci such that distance is positive. So we can define fx equal to summation of that. And there is no important of this 1 by n. Suppose you assume fx equal to only this summation excluding that 1 by n. Then the proof will be the similar thing. The only change part will be this one. So here this part will be same, and here that fx will be greater than epsilon, right? And this part will be same. So it will be, there will be no n, that will be epsilon greater than epsilon. So the proof will be the same one. And here we will have something. Now f has a smallest element, right? So now in this case, we will assume not delta, we will assume some number delta dash here. And that Lebesgue number will be that delta dash by n. So if you assume fx equal to only this summation excluding that 1 by n, then what you have to do, you have to choose the smallest element delta dash, and then you have to choose delta equal to delta dash by n, and that delta will be my Lebesgue number. See, in that case, what will be my f of x0? F of x0 will be less than equal to n times, right? N times x0 cm. And what will be my fx? Fx0, and fx0 will be, in that case, f of x0 will be bigger equal to n delta. Why n delta? Because f of x0, right? What is the least value of x0? That is delta dash, and we have assumed that delta equal to delta dash by n. Therefore, f of x0 greater than n delta, greater equal to n delta, and here also you will have n x0 cm. So we will get the same inequality, that d x0 comma cm greater equal to delta. So there will be nothing. So all the proof will be the same. So there is no tricky part here. You have to just choose this summation. That's all. And once you choose this summation, then all the proof will come automatically. So first of all, you have to choose one B with delta, right? So where is my B? So not this one. Fine, from here, right? So we have to choose one function, one set B whose diameter is less than delta, right? Then we will show that B is subset of AM or some AI via this ball. So we need to choose one ball. So we first choose one x0 from B and find one ball, this one. And then we will find B subset of this ball, and this ball is subset of some AM. And then it will prove that B is subset of AM. So the proof is actually simple. There is no tricky part. If you assume fx equal to either this term or excluding that 1 by n, then the proof will come automatically. So here I shall give one homework. Now assume fx equal to only the summation of I equal to 1 by n d of x comma ci. Okay, and try to prove the lemma. See, I have already explained the proof. So there will be, all the thing will be the same. You have to only choose this delta dash, and this will be automatically same. So this is your homework. So see you in the next video. Fine.